Okay, before we get started, I got a question from somebody yesterday. I don't know if this person is already here or not. No, I think that he's not here yet. So let's wait another minute. Okay, I think that we can get started. So remember that I think yesterday we wrote down the Boltzmann equation for tensor perturbations. And yesterday I also told you that if you want to obtain the hierarchy for the different momenta of the perturbation field, you might either use the conservation of the stress energy tensor, something that you did yesterday afternoon when you derived the fluid equations from the conservation of the stress energy tensor, but you could also appropriately integrate the Boltzmann equation over d3p in order to obtain the different momenta. For example, you can integrate this in d3p weighted for the energy if you want to obtain an equation for the density perturbation, which is the first moment of the Boltzmann hierarchy. So what you do is simply integrating each of these terms in the usual d3p, then wait for E, and then apply all of the different terms in the equation. Now, you can expand then the integral in radial coordinates, and this will single out an integration over the solid angle, of course, at some point. Then you can easily convince yourself that when you integrate this term over the solid angle, because of this factor here, which is either cos to phi or sin to phi, you might have a vanishing integral when you apply the integration over d phi from 0 to 2 pi. This is actually true. It doesn't apply to the full Boltzmann hierarchy, though, because when you obtain the different momenta of the hierarchy by integrating over d3p, you don't integrate only over d3p, but you have to apply the proper weight when you want to single out the different momenta. For example, this applies when you want to obtain an equation for delta. Then if you want to obtain instead an equation for the second moment, which is the velocity field, then the weighting function will be the I component of the momentum, sorry. And then again, you apply everything here. And of course, you can go down and obtain an equation for the anisotropic stress. And in that case, the weighting function will be something like this. So depending on which moment of the hierarchy you want to obtain from the integration of the pure, let's say, bare Boltzmann equation, then the integration over the solid angle might be slightly different, which means that it is not always true that the integration of the metric part of the Boltzmann equation will give you a vanishing result. In case of photons, we can see probably later, either today or tomorrow, that the only moment of the hierarchy, of the Boltzmann hierarchy, that will retain the metric part of the Boltzmann equation will be the one with L equal 2, so the quadruple moment, which is obtained from the integration that gives you an equation for the stress, for the anisotropic stress. And this tells you also another interesting result, that in case you are handling a species which doesn't have an anisotropic stress, for example, we have seen that a non-relativistic species, for example, cold dark matter, doesn't have an anisotropic stress. Remember, because the mass, the energy of the species is the mass, which is much larger than the moment, so this integral will vanish. So in case of this species, which doesn't have an anisotropic stress, it means that the Boltzmann equation for the anisotropic stress part will be an homogeneous equation, which means that for those species, you won't need an equation nor for the anisotropic stress part, nor for the higher momenta of the Boltzmann hierarchy. This is another way of saying that for non-relativistic particles or for perfect fluids, for example, the one that you saw yesterday, you can cut the Boltzmann hierarchy to the first two moments of the harmonic expansion. So you only need an equation for delta and an equation for the velocity. For ultra-relativistic species, or species that have a non-vanishing anisotropic stress, then the hierarchy also need to retain momenta which are L equal 2 or higher. And in that case, for L equal 2, you will have the source term in the Boltzmann equation to be given by the metric part of the tensor perturbations. So if you prefer, we can discuss this later offline, but I hope that at least I partly answered the question that I received yesterday. And I thought that it would have been useful also to discuss this with you, because it provides you some interesting results. So now let's go back to where we were yesterday. Let me briefly recap what we saw yesterday. We saw that we can describe the CMB is polarized. So a useful formalism that we can use to describe the CMB makes use of the Stokes parameters. The Stokes parameters that we will consider in our case are the temperature, which represents the total intensity of the field, and then the two Stokes parameters that describe the degree of linear polarization of the CMB, Q and U. We have seen that T is a scalar quantity, so T has a definite spin, is a spin zero quantity. Therefore, we can expand the T field in spherical harmonics. This is useful because it allows us to handle more easily the angular dependence of the field, and the usual expansion is done with the usual spherical harmonics that you might have seen in other occasions. And so let's write the T field as a sum over the L and M moment of the expansion, where the basis is provided by the usual spherical harmonic functions, which encode the dependence on theta and phi. And the expansion coefficients are these AT LM. Then we have seen that Q and U, unfortunately, don't have a definite spin, so we need to manipulate a bit Q and U in order to obtain quantities that have a definite spin and can therefore be expanded similarly to the TKs in spherical harmonics. We built these two quantities, Q plus IU and Q minus IU, and we have seen that these two quantities are a bit more complicated than T because they are not scalars. They are so-called spin-2 quantities. And so when we expand them in spherical harmonics, we cannot use the usual spherical harmonics, but we have to use this expanded version of the spherical harmonics, which are the spin-weighted spherical harmonics. So we use the spin-2 spherical harmonic for Q plus IU, and the spin minus 2 for Q minus IU. It might seem complicated what we've did so far, but this is useful because it allows us to expand these quantities and so to treat more easily their angular dependency. Now we have another issue though, which is an observational issue. Remember that Q and U represents the degree of linear polarization. Q is the linear polarization along XY axis, and U is the linear polarization along 45-degree directions in a given reference system. So if you need to define Q and U, you need to define a reference system, and this reference system might not be the same for all the different directions that you have to observe the sky in order to obtain your CMB maps, for example. Or, in other words, if you fix a reference system which is consistent with the system in which you are observing, then you have to translate or you have to move all the Q and U that you observe in a local reference system to your own reference system. So this means that treating the polarization part of the CMB with Q and U might be problematic because we have every time to convert the quantities that we can define locally on the sphere as Q and U into our specific reference system that might not be the same of the local reference system that we defined on the sphere to obtain Q and U. So we might need something that is more similar to T. We would like to handle a scalar quantity instead of using these spin two quantities which have a strong dependency on the reference system. And we can do that by using the properties of the spin two, or in general of the spin-weighted spherical harmonics, which are represented by two peculiar operators. They are the so-called spin-raising and spin-lowering operators. And thanks to these operators, so let's call this a spin-raising operator. Suppose that we apply the spin-raising operator to a given spin quantity. This operator would act in such a way to increase the spin of the function to which it is applied by 1. So when you apply this operator to a given function f, which has a definite spin, remember that a function f with a definite spin has the property of transforming as in this way when you rotate the reference system. So if you apply the spin-raising operator to such a function, then you are increasing by 1 unit the spin of the function. Similarly, we can define a spin-lowering operator. And as you can easily imagine, if you apply such an operator to the same function, then this will decrease by 1 unit the spin of the function. So you can already see where we are going. We have two functions which have spin 2 and spin minus 2. We would like to convert them into something that has spin 0, so that is a scalar. What we can do, we can apply twice both these operators to the proper combination of Q and U, and from these two quantities, we obtain the two scalars that we prefer to handle when we treat the depolarized CMB. Let me give you also the expression of these operators. So the spin raising 1 is given by, no, maybe I need a bit more space to write it, so let's use the other blackboard. So the spin raising 1 is defined in this way. Remember that theta and phi are the angular dependency. So this is the spin raising. And the spin lowering is very similar. We'll just have minus S here. Minus here. And a plus here. So we want to apply these operators twice. So what we will care more will be, for example, the twice acting spin raising operator that we will apply to a spin minus 2 quantity, because from minus 2 we want to increase it to 0. And so if you apply this twice with S equal to minus 2, if you want, you can do the calculations, but I will give you just the final result. Remember that we call mu cos theta. So the twice acting spin raising operator will be given by this expression. And similarly, we want to apply twice the spin lowering operator to a spin 2 quantity. And so every time we need to apply this operator twice, we effectively have to do the following operations. To the spin 2 quantity. So this M here stands for the derivative, comes from the derivative with respect to phi, because if you imagine that F can be written, that the phi dependence of F can be written as the exponential e to the im phi, every time you apply a phi derivative, you effectively take down the m index of the phi dependence. So this is why you have an m appearing here. Okay, so the two quantities to which we want to apply twice the spin raising and spin lowering operators are Q and U. If we do that, we obtain two scalar quantities that we can finally expand in the more easy to handle usual spherical harmonics, the same that we used to expand the T field. So if we apply twice the spin raising operator to, of course, Q minus IU, which is a -2 quantity, then all this function here will be a spin 0. So we can expand this in spherical harmonics with just the caveat that here we have this bizarre prefactor These are factorials. A2 is just an expansion coefficient. So the spin racing, when we apply the spin racing to Q minus IU, this is not going to be applied to the expansion coefficient, but is going to be applied to the spin 2 spherical harmonic. So this is where this operator here is acting. And when we apply the spin racing operator twice to the spherical harmonics, we take out this prefactor here, and we remain with the usual spherical harmonic that we used also for T. So the combination of this prefactor and this spherical harmonic comes from the application of the spin racing operator twice on the spherical harmonic of spin minus 2. Then the same can be done for the spin lowering, that at this point we apply to Q plus IU. And again, this operator will not act on the expansion coefficient, but it will act, sorry, this is of course minus 2, will act on the spherical, on the spin 2 spherical harmonic. And so when we apply that to the spherical harmonic, we again extract the prefactor. We have the expansion coefficient that remain the same. And finally, we can use the spin 0 spherical harmonic. So we have finally arrived to the scalar quantities that we want to use when we describe the CMB polarization. And let me call them not these two, but let me define two other quantities which come from the combination of these two. So from the combination of the two scalars that we've just defined, let me define another scalar quantity, which is E, the E field. And the E field will be written in this way. We retain the prefactor. We define this new expansion coefficient, which is AE-LM. And the expansion basis is again given by the spherical harmonic. And this expansion coefficient EA, let me define it as minus the sum of the two expansion coefficients that we used for expanding the two scalars Q minus IU and Q plus IU. So you see that the E mode, or the E scalar quantity, is basically obtained from the summation of these two old scalar quantities that we obtained from the spin raising and spin lowering operators. I can, of course, define another scalar quantity, which is B. B is still expanded with the same prefactor here. in spherical harmonics. The expansion coefficient is B. And the basis, since this is a scalar, is of course the usual spherical harmonic. And from this we can define B in terms of the old A minus 2 and A2. And this time B will be given by I, the difference between the two expansion coefficients. And so from this, you see that the B field is obtained from the difference between the two scalar quantities that we got from the spin raising and spin lowering operator. Also, note that from the definition of the new expansion coefficients, the one for the E field and the one for the B field, we can see that E is a pure scalar, similar to T. So if we apply the parity operator to E, this will remain the same. So it is a pure scalar. This is not true for B, which is instead a scalar, but it is a pseudoscalar. Because if you apply parity to B, this will change sign. Now, this is an important property because in the early universe, at least if we consider the standard cosmological model, we do not expect sources of parity violation. So we will not expect the cosmological probes that are generated by physics acting in the early universe to generate parity violating probes. This means that whenever we consider cross-correlations between the three fields that we can define out of the CMB, the T field and the two polarization fields, E and B, then we also expect that the cross-correlations involving scalar and pseudoscalar, so TB and EB, will be vanishing. So in the standard cosmological model, the power spectra or the cross-correlations between T and B and between E and B are expected to be 0. And this gives us a handle, an observational handle of physics beyond the standard model, because suppose that some CMB experiments is able to measure with statistical significance a signature of non-zero TB or EB spectra, then this means that there is some physics at play in the early universe that is generating such parity violating cosmological probes. So the fact that the standard cosmological model has these strong predictions of TB and EB equal to 0 gives also us a way to go for beyond standard model physics by observing these additional properties of the CMB. Then just a note on the fact that we identify these two scalars that we use for describing the polarized CMB as EMB. Why we use the same expressions that we use for electric and magnetic field. You can think of this as coming from the decomposition of the polarization tensor. Remember that we started from the PAB tensor that we wrote yesterday, which has T plus Q and T minus Q on the diagonal and minus U on the off-diagonal terms. Then, as any other 2x2 symmetric tensors, PAB can be decomposed into a trace and traceless part. And the traceless part can further be decomposed in a similar way in which you usually decompose a vector field. So you can write a vector field as the gradient of some scalar and as the rotor of some other vector fields. And this very same decomposition applies to the traceless part of the polarization tensor. And these two scalar fields that we have defined here are intimately related to the gradient part and the rotor part of the decomposition of PAB, and therefore the gradient part is identified as E, which is the analogous to the electromagnetic formalism, and the rotor part is identified with B. So this is just to tell you why we use this notation in analogy with electromagnetism. Okay, so now we have defined some easy to handle quantities. Remember that these are the fields, but we are not interested in the specific values of these fields because they arise, as we said yesterday, they arise from a stochastic process. So instead of being interested on the individual values of these fields, we are mostly interested in the statistical properties of these fields, and since they are Gaussian, we are interested in their variance or in their power spectrum. So what we want to compute at the end, let me call with X whichever T, E, and B. So what we would like to compute at the end is the ensemble average of possible correlations between these fields. Now, let's use for X the spherical harmonics decomposition that we have just defined there. So we need to expand X in spherical harmonics, and so we have one sum. Then we have to expand X prime in spherical harmonics, and so we have another sum. Then we have the expansion coefficients for the two. And then we have the two spherical harmonics. Here. Now, how can we simplify this expression? We can make use of the statistical properties of these fields. We can use first that these are independent random variables. And so we do not expect any, yes?
I understand if the angle variables are different for the two fields.
Yes, it's theta phi and theta prime, sorry. There is a prime also here, I was sloppy with the notation, yes. So we can use that those are independent random variables, and because they are independent, we do not expect any non-vanishing correlations between different multiples. So when we compute this variance, we do not expect to have off-diagonal terms in this variance. You can think of this variance as a huge matrix with L and L prime as rows and columns, and we do not expect any correlation between L and L prime that are different. So we expect a Dirac delta in, a Kronecker delta in L prime to appear. We can also use that the fields are rotationally invariant. And this will give a condition on M and prime. So because these are rotational invariant, we don't have a specific dependency on M. which represent the dependency of the field or the behavior of the field under rotation. And so we again expect an MM prime to appear. So if we use these two conditions to simplify the expression of these variants, then we can write that ALM, AL prime, M prime is proportional to these two deltas. And the proportionality constant is exactly the variance of the field that we call CL, that we also call the power spectrum of the specific combination of the fields that we are correlating here. If these are X and X prime, this will be the power spectrum of XX prime. So, if we sum over M on both sides, then using the fact that here we have a Dirac delta, a delta in MM prime, then you can easily convince yourself that CL is 1 over 2L plus 1, the sum over M of the cross correlation. So now we use this expression into the line above, and we also use a property of the spherical harmonics. Remember that there we have a product of the two spherical harmonics. Sorry, this, I also forgot another thing, that this should be like this. We have the product of the two spherical harmonics, and we can use a relation between the spherical harmonics and the Legendre polynomial. Remember that we also expanded the angular dependence, the mu dependence, which is the theta dependence of the fields in Legendre polynomial. And there is indeed a relationship between the two, because the Legendre polynomial of order M can be expressed as a function of products of spherical harmonics. And the expression is the following. So we have 4 pi divided 2L plus 1. Then we sum over M. And here we have the product of spherical harmonics. This is Lm, and these are instead primed. So if we combine these two expressions, we use the expression of the ensemble average in terms of the power spectrum, use the property coming from randomness, independency, and rotational invariance, and we substitute the sum over the product of the spherical harmonics with the Legendre polynomial. Then we can rewrite the cross correlation between the two fields X and X prime in a very simple way, which just involves, instead of using spherical harmonics and ensemble average, it just involves the power spectrum and the Legendre polynomial. Sì, che ho fatto? Yes. because exactly I guess that the summation will just cancel the theta prime and phi prime dependency. It's a good question.
I think that because the general rule is that the first spherical harmonics is dependent on the n direction, and the second one on the n prime direction.
Yes.
Which is defined as the
Yeah, and yeah, exactly.
n and n prime.
Yeah, thanks. Correct. So this will be, let me just write this. Yes, but since these are scalar quantities, you can see that they must obey, that there must be a condition that the coefficients has to obey when they are taken as complex, because the field that you are expanding is a scalar. So it's true that this one must be a complex one, but you can also write the complex in terms of the opposite, non-complex one with flipped indexes here, because the field is scalar, and then you take the summation. So yeah, in general, this must be complex, but I was just being sloppy. Okay, so if we take everything together, then we have that the ensemble average can be simply written as a sum over L with a given prefactor that depends on L, the power spectrum of x prime, and the basis that we use is the basis of the Legendre polynomial. You can also think of this as a relation between observational quantities and theoretical quantities, because it's much more easy for us to predict CL. So when we derive theoretical predictions of the CMB, we evolve an Einstein-Boltzmann code, and the output of the code will be the power spectrum or the power spectra of the CMB. Of course, not just the CMB, all the other cosmological probes that you can think of, but as far as we are concerned, the theoretical prediction is encoded in this power spectrum. But when we observe the CMB sky, of course, we don't start from the power spectrum. We don't observe directly the power spectrum. Instead, we map the T, E, and B fields. In reality, we map T, Q, and U. Then from Q and U, manipulating those maps, we obtain E and B. And from maps of T, E, and B, we can reconstruct the correlation between the different maps. So the observations sit here, and this gives us a way to relate what we observe with what we predict. Okay, I think that this is maybe a good time to have a break before we get started with the the Boltzmann formalism for the CMB. So I will have a break until 10-ish and take any questions either here or from Zoom. Okay, now we'll start with deriving Boltzmann equations for photons. And you have several ways in which you can derive the Boltzmann hierarchies for photons, both for scalars and tensors. And you can see them in different textbooks. So here, I will use a classical approach, which makes use of the formalism for the radiative transfer. Assume that the starting point for our derivation is the radiative transfer equation, which describes the variation of the intensity, generic intensity, so it includes both the proper intensity and the polarization part. The variation of this intensity as this radiation travels along the line of sight. And you can usually write this as, let me use C for the proportionality constant. So the variation of the intensity is given by drag term, so something that is depleting the intensity of the radiation, because, for example, you have scatterings. So here you will have the scattering cross section. So while this radiation is traveling, it scatters off target particles, in our case, free electrons. So you can think of the CMB that is propagating, and while it propagates, scatter of free electrons. And so the intensity is depleted because of this scattering, so it's lost. Plus some source term. It can happen that there is something that is giving additional power to this radiation, and this is encoded in this source term. And in our case, this will be again given by scattering, but in this case, these are not scattering happening along the line of sight, so scattering that make the scattering radiation lost, but these are scattering that are happening from other directions and are therefore channeling the intensity along the line of sight that we are considering. So in the case of the CMB, we can write this as tau prime I will come back in a moment to tau prime, minus the source term that we write in this way, tau prime over 4 pi. We are integrating over the solid angle because we want to capture all the scattering that are happening over the solid angle and are channeled in the direction that we are looking at. Here we have the tool that we need to relate scatterings from different directions into the direction that we are looking at. This is the scattering matrix. And what is scattered, of course, is still the intensity at a given direction. Tau prime is the differential optical depth and is defined as the integral from a given time to the current observational time of the density of scattering targets, in our case, free electrons. So NE is the density of electrons, but not all of the electrons are available for scattering because, for example, they are starting recombining with protons into neutral hydrogen, and therefore we only have a fraction x of the total density of electrons available for scattering. Then we have, of course, the scattering cross-section, which in our case is the Thomson scattering, integrated over dt. So sorry, this is not tau prime, this is tau. This is the optical depth. And from here, you can see that tau prime is simply minus the density of target times the cross-section. Okay. Now, before making explicit what all the different terms are, I'd like to spend a few words on the scattering matrix. You can find the full derivation of the scattering matrix, for example, in the book by Chandrasekhar, Radiative Transfer. It's not a complicated derivation, it just involves some reference system transformation, some angles consideration. So I won't derive the explicit form of the scattering matrix. We will just retain what is needed for our calculations, but I'd like just to sketch how you can derive the scattering matrix. So the scattering matrix, as I said, is telling you how the different scatterings that are happening over the solid angle are channeled through the directions that we are looking at, that we are interested in. And so it, of course, involves the usual relation between the two scattering waves. So we know how to relate scattering, the incoming radiation and the outgoing radiation when scattering happens. And we know how to do that in the scattering plane that is defined as the plane of the two direction of incoming and outgoing radiation. So if you have some radiation that we define as M prime that is moving along this direction and is scattering with a given angle theta and produces some radiation N that moves along this other direction, then we know how to relate the outgoing radiation to the ingoing radiation in this specific plane, because this will be given by this matrix R theta. And R theta will be a 3×3 matrix, which has cos square in the first entry. It's a diagonal matrix, has cos square in the first entry, 1 in the second diagonal entry, and cos theta in the last entry, and 0 here. Why? Because we can think of this vector n that represents the incoming and outgoing radiation as having 3 components. One component that is the radiation along the scattering plane. The second component is the radiation perpendicular to the scattering plane. And the third radiation is the product between the fields along and perpendicular, if you want. So this will effectively, if you remember the definition of U, this would effectively be proportional to the U component of the polarization. So this is the relation that we know exists between incoming and outgoing waves in the scattering plane, but in the reference system, in the generic reference system that we will consider, the scattering plane does not coincide necessarily with our own reference system. So we need first to make an angular transformation, because from our chosen reference system that we use to observe and describe the scattering, we need to move to the scattering plane reference system. Then in this scattering plane, we can write the relation between incoming and outgoing radiation. And then once we have done that in the scattering plane, we have again to go back to our reference system. So if we write all these transformations together, n is the outgoing radiation, we have to start from the ingoing radiation. We first have to move from our reference system to the scattering plane reference system. Let me call this transformation as L minus I1, where I1 is an angle or is a set of angles that allows us to to move from one reference system to the other. I'm using this notation because it's the same that you can find in Chandrasekhar if you want to go through the full calculations. Then, once we are in the scattering plane, we can apply the matrix that tells us the relation between incoming and outgoing radiation. And then we have to move back again to the reference system, where pi is exactly the angle pi. So this series of transformation involves moving from the spherical coordinate system to the scattering plane, then back again to the spherical coordinate system. So it has some algebra of trigonometric functions involved, but at the end, we will not be following all these calculations. Let me just add that this I1 angle is the angle between the scattering plane, let me call it SP, and the meridian plane of the incoming radiation, so is a prime. Theta is the scattering angle. And this other angle here, pi minus I2, is analogously to the transformation that we have done here, is the angle between the scattering plane and the meridian plane of the outgoing radiation. So once you do all these calculations, you can prove that your scattering matrix that will eventually depend on mu and phi in the direction that we are looking at, and mu prime, phi prime, which are all the possible directions that we are integrating over with the solid angle, can be decomposed into a sum of different matrices. And this decomposition is very useful because each of the terms of this summation has a very specific dependence on both mu and phi angle. So this can be written as an overall matrix Q, which multiplies a matrix that we call pi 0. And pi 0 only depends on mu and mu prime. So pi 0 doesn't have any dependence on phi, and you can think of this as if you were expanding this matrix pi 0 in M harmonics, you will have something like e to the I m phi minus phi prime with m equal to 0, so no dependency at all. Plus something with a prefactor here, which is 1 minus m square, which multiplies 1 minus m prime square root of this product. And then we have P1, which in this case depends on all m, mu phi and mu prime phi prime, but this depends on phi minus phi prime in a similar way with this time m equal to 1. So if you were to expand this matrix into harmonics, into m harmonics, which involves the difference phi minus phi prime, you will only retain terms that have m equal to 1. So in fact, it is not a full expansion, but this will just give you one specific term of that expansion with m equal to 1. Plus, so this was m equal to 0, plus P2, and P2 also depends on mu phi mu prime phi prime. And similarly to pi 0 and pi 1, if we expand pi 2, then this pi 2 will only have terms with m equal to, plus minus 2, and this is the same, m plus minus 1. So these two matrices will be given by the sum of terms with m equal to plus 1 and minus 1, and plus 2 and minus 2. The other important feature of the scattering that we are considering is that this kind of scattering does not mix together different dependencies on mu phi, mu prime, phi prime. So we can always separate and factor out these different dependencies. This will simplify a lot the calculations. And using the properties of this decomposition of the scattering matrix, we can derive some useful expressions that we will need lately. We can consider, for example, the integral over phi prime of the first term of the scattering matrix, so pi 0 mu mu prime integrated with a factor which is e to the I mu prime phi prime. And since this has only terms, can be written as terms which have only m equal to 0, then you can convince ourselves that this is simply 1/2 pi 0 can be taken out because it doesn't have any dependence on phi. And here we will have a delta of m prime 0. So whatever m prime here is different from 0, then this integration will give us a vanishing result, unless m prime is equal to 0. Now let's do the same for the other terms. I will do this for pi 1 as well, but let me just write the dependency as omega and omega prime. Then we have e to the m prime phi prime. I will write this for pi 1, even though at the end we will never use pi 1 in our calculations, but just for the sake of completeness. Remember that pi 1 is just the sum of two terms, one with m equal to +1 and another with m equal to -1. Then let's use the fact that, as I told you, the scattering doesn't mix mu phi, mu prime, phi prime, so we can factor the expression of pi 1 into terms that have only mu and only phi dependency. And so at the end, when we do this integration, we end up with one matrix that only contains terms that depend on mu and mu prime, with some dependency on phi that we can factor out. And here, we only have something that remains if the m prime that we are integrating over is equal to 1, plus something similar to this that applies to -1. So we will have a similar matrix, pi -1, which only depends on mu and mu prime. We will have a phi dependence, this time with minus that we can factor out. And then we have the delta, which only retains m prime equal to -1 terms. And these two matrices here are related because, let me write this up here, because pi 1 is just pi -1 complex. And finally, the other expression that we need is the one for pi 2. And this is the same coefficient. Here we also have one matrix that only depends on mu and mu prime, and we call it pi 2. We also have the dependency on phi that we can factor out in this way. And we have the delta between 2 and m prime, and the same for pi -2. Okay, now let me give you the full expression for some of these matrices that we will use in our calculations. I will give you the expression of the only matrices that we will use, so I will neglect pi 1. Now, the matrices that we will need are Q, which is a very simple matrix, is a diagonal matrix, is a 3 by 3 matrix, diagonal with 1, 1, 2. Then we need pi 0, which is again a 3 by 3 matrix with these values as entries, so 2, 1 minus m squared times 1 minus m prime squared plus m squared m prime squared, mu, sorry. Then the other element is mu squared and 0. Here we have mu prime squared, 1, 0. And the third line is just 0, 0, 0. And finally, we need pi 2. Which again is also equal to pi minus 2 complex. And this is 1/2, again a 3 by 3 matrix with mu square, mu prime square, minus mu square, minus I mu square mu prime. The other row is minus mu prime squared. 1 I mu. And finally, the third row is mu prime square minus I mu prime. Okay. Now we have all the ingredients that we need to finally get started with writing down Boltzmann. Actually, there is another thing that we need, because the generic expression of the Boltzmann, of the transfer, radiative transfer equation that I wrote a few blackboards ago, is valid if we consider system that is at rest. However, due to perturbations, we know that there is a relative velocity between the two main fields that we are considering in this formalism, so photons and electrons. So the radiative transfer equation that I wrote before must be amended to account for this relative velocity between electrons and photons that is responsible for a sort of Doppler effect. So the other term that we need to add is a Doppler effect. And in order to write the Doppler effect, let me also define VB, which is the velocity of the electrons. I use the B subscript to refer to baryons. You said yesterday that we refer generically to electrons and protons as baryons in the early universe. And of this VB, for our treatment, we only need to retain the component that is aligned with the k direction, so with the Fourier mode direction that we consider. So we can write VB as the magnitude of the velocity with the direction that is specified by the k mode. So whenever we have to compute, and this will happen whenever we have to compute the scalar product between the baryon velocity and the photon momentum direction, then this is simply VB k scalar p, but we have already defined k scalar p as mu. So this is VB mu. So now we can write the Doppler effect, because if we again refer to n as the vector that is defining our radiation, then n Doppler can be written in this way. We can take the derivative of n with respect to the momentum. So we can expand this in this way, where this variation of the momentum is due to Doppler, and we know how to write this for a wave that is undergoing a Doppler effect, because this will be simply given by P tilde at the product between the direction of the momentum and the relative velocity that is responsible for the Doppler effect. So we have to take the scalar product because, of course, for Doppler, we are just interested in what happens along the direction of propagation. And so with the definition that we have defined above, we have that the Doppler term can be written as the derivative of our vector for the radiation times the momentum. Remember that P tilde is the new variable that we use for the momentum, which is the physical momentum times the scale factor, would be mu. So this is the Doppler term that we retain to amend our radiative transfer equation. Now let us write the amended version of the transfer equation. We have that dN over dt is tau prime n, so is the depleting term of the radiative transfer equation due to scattering along the propagation that actually depletes the radiation, times, plus, actually with a minus because of the way we have defined the differential optical depth. So minus tau prime over 4 pi, the source term, that is our scattering terms obtained with the scattering matrix, times the Doppler term. So let me write this delta n Doppler. With, of course, the tau prime, because we are still considering that the Doppler comes because of the scattering. So it has the same sign of this term. Now let's move to Fourier space. Let's move to conformal time. So instead of using t, let's use e. And let's remember that this term here, basically, this is the total derivative with respect to time of whatever function we put here, which can depend on different variables. We know the expression of the Liouville operator in a perturbed universe in terms of scalar and tensor perturbations. So now you can understand why we made all the efforts in the previous lectures to derive the form of the Liouville operator in case of scalar and tensor perturbations. So this total derivative with respect to time can be now made explicit depending on which kind of perturbations we would like to consider first. And remember that we can treat scalar and tensor separately because of the decomposition theorem that holds at least a linear order. So we will do this first for scalars, and we derive the Boltzmann equations for the photon fields in case of scalar perturbations, and then we will repeat the calculations for tensors. So first, let's focus on scalars, and let's also consider that the Doppler effect, because it arises from the interaction between the relative velocity between photons and electrons, just applies to the scalar case, so we will not consider the Doppler in case of tensor perturbations. So let's first focus on scalars. Let's keep the Doppler term, and let's rewrite the total derivative as the Liouville operator in case of scalar perturbations, moving to conformal time, moving to Fourier space, and using the p tilde variable that we have defined yesterday. So when we do all of these operations, we end up with this equation for and let me also add that we will use, instead of this total n, an expansion of n because of perturbations. So similarly to what we did for the distribution function that was expanded as the sum of the equilibrium distribution plus a small perturbation around the equilibrium distribution, we can do the same for the n vector that we use to identify, to describe, the CMB field. So we write n as the sum of n0, which is the unperturbed CMB field, and as such, it doesn't have polarization. So the n0 is very simple. Let me write this. N in general is given by these expressions here. I just sketched that when we started discussing about the scattering in the scattering plane. So the first entry is the polarization along the scattering plane. So it's T plus Q, is the T plus Q entry of the polarization tensor. The second entry is T minus Q. And so this is the polarization in the longitudinal direction. And this is the second diagonal entry of the polarization tensor. And finally, the third entry is the U component of the polarization field. So if we write N as the sum of an equilibrium term or unperturbed term plus the perturbation, then it's easy to convince you that this N0 doesn't have polarization, because we saw that polarization is sourced because of perturbations. So this N0 can be written as a coefficient which multiplies a simple vector which is 1, 1, and 0. And let's call this vector U. Then this N1 will have all the perturbation effects inside. So when we use this decomposition and write the Liouville operator and insert the decomposition into the Liouville operator, remember that we only have to retain linear terms, and in fact, we arrived yesterday to an expression for the Liouville operator with only linear terms, and the equation above becomes derivative with respect to conformal time of the one component, so the perturbed component, plus I, k, mu, n1 minus A tau prime, where A is the scale factor. And from now on, I will just refer to this product as tau prime. So I will incorporate the scale factor into the definition of the differential optical depth equal to phi prime, where this is the derivative with respect to the conformal time, plus I, k, mu, psi, plus A tau prime VB mu. I will write the expression with all the A now, and then I will forget about it. Then here we have P tilde dn0 over the P tilde, because all these other terms here are linear, so here we just retain the first order, minus A tau prime over 4 pi, and here we have the scattering terms. So integrated again over the omega prime scattering matrix n1 omega prime. So before ending the lecture, let me just take 2 minutes, because I want to tell you that we can further simplify this expression by noting the following thing. So first, let's rewrite this product here, pi tilde times the derivative, as n0 times f0, where f0 is the logarithmic derivative of the distribution, unperturbed distribution with respect to pi tilde. So this will just lighten a bit the notation. Then we note that the only explicit dependence on pi tilde comes exactly from this product. There is no other dependency, direct dependency on pi tilde that arises from any other of these terms in this radiative transfer equation. So we can factor this dependency out. Then we can expand the phi dependency. Remember that N1 depends in general on mu and phi. We can factor out the phi dependence we can expand, the phi dependence in harmonics. So let's write N1 in this way. N1 depends on mu, phi, pi tilde, and eta. Let's write, yes, N0, F0. So the pi tilde dependency comes from this prefactor here, which is the only explicit dependence. Then we expand over M the phi dependence, and we only retain here a vector which depends on the conformal time and mu. Why this expansion is useful? Because when we insert, first of all, when we insert this expansion into the full equation, we can factor out the N0, F0 term. So this will disappear from the equation and will simplify our notation. So we only remain with an equation for this expansion here. When we insert this expansion into this integral, you see that here we will have the integral over the different pieces of the scattering matrix times this factor. This will give us a factor that is EI m prime phi prime, because n into the integral depends on the primed solid angle. And remember that we know when we expand the integration over the solid angle and we extract the integration over phi prime, we know how the different pieces of the scattering matrix behaves when we integrate over phi prime times this factor here. So this is telling us that when we insert this term here, only pieces which have m the absolute value of m less than or equal to will survive into this integral. Because all the others, once we perform the phi integration of the different pieces of the scattering matrix times the m prime dependent factor, will just vanish because of the delta between m prime and the coefficients that come from the expansion of the scattering matrix. So eventually, N1 So eventually, what we need when we solve these equations are just terms that come from m less than or equal to. All the terms with yeah, exactly. All the terms with m greater than 2 will still remain in this expansion, but when we write the equation for those terms, they will not take any contribution from this integral. So what I'm saying is that only terms with m less than or equal to can have the full expression of this equation, which takes contributions also from the integral of the scattering matrix. All the terms with m larger than 2 will not have any contribution from this term here, and so they satisfy an homogeneous equation from the expression here. So if those terms are 0 in the early universe, they will remain 0 as they evolve according to this equation, because they will not have any non-homogeneous term that can source their non-vanishing value during the evolution. So at the end, we can only focus on terms that have m less than or equal to when we derive the expression of the Boltzmann equation for scalar perturbations. Now let me end here, and let me know if you have any questions.